Okay, intro to limits. We are getting really close, and hopefully that terrible joke will make sense here in a minute. What is a limit? Let's first talk about what a limit is and why we care about them. A limit is a way of describing the behavior of a function as x approaches or gets close to some value. Okay, so let's suppose that we had this graph over here and we picked some arbitrary a, some value a, and we wanted to know, well, what is the graph doing as the x values get really close to a? So as we come in we get closer to a from the left, and as we come in and get closer to a from the right, what is happening to the function values or the y values? Right? And so the way that this notation is read is the limit of the function as x approaches a equals L. And we'll look at a bunch of examples like this. But you want to remember that limit of the function as x approaches a equals some value L. And that L is a y value or a function value. Let's go a little bit more into why we care. Well, consider this problem right here. F of x equals x squared plus x minus 6 divided by x minus 2. If I tried to evaluate the function at x equals 2, I couldn't. I'd be dividing by 0. But you and I both know that that function is doing something at x equals 2. It's not like there's a big, giant, gaping, hole in the graph from negative, 10 to 10 or something like that. There's a little hole, but we want to be able to describe the behavior at x equals 2. So by taking the limit at x equals 2, if I was to draw in, here's 2, and so here's the behavior of the function here, and we know there's an open hole, right? But if I wanted to look at the behavior, I could come in from the left on the function, I could come in from the right, and by kind of wedging into, kind of looking at what the graph is doing to either side and getting really close to that x value, I can tell you that that graph approaches 5 or gets really close to 5. So there will be more complex examples, but that's the basic idea of how limits can be useful. Getting really close to something that may not exist if we just try and evaluate right away. Let's look at a situation where the kind of the most basic situation that you'll come across in limits. Suppose I had this function here, and I wanted to take a look at the limit as x approaches 0. The first thing that you should always try is just direct substitution, where you just evaluate f of 0 and see if that works. In the previous example, that didn't work. In this one, though, I think it will, because if I evaluate this, f of 0 is equal to, well, 0 minus 0 plus 1, which is just 1. Okay, so f of 0 is 1, and if we look at the graph, the function, as we come in to 0 from the left and from the right, approaches x or y equals 1. So we say the limit as x approaches 0 of the function is just 1. Alright? So first thing you should always try is direct substitution. That's not always going to work though. Let's look at some examples where we just analyze limits graphically. This will give us an idea of how we approach limits and how we can use graphical techniques to solve limit problems. So suppose this is my function over here on the right. It's a piecewise defined function, right? So it's broken up into a bunch of little chunks. Let's first look at f of 0, the function value at 0. Well, the function value at 0 is just 1. If I want to know what f of 0 is, it is not 0. The point 0, 0 does not exist on the graph. It is just 1. So f of 0 is 1. Now the limit as x approaches 0 of that function, well, that's where I'm going to come in from the left-hand side of the graph. I'll come in from the right-hand side of the graph. And notice that both sides get really close to 0. So we say the limit of the function as x gets really close to 0 is 0. Because the behavior, or because the graph is approaching 0 at those points. All right, let's look at then the limit as x approaches 0.5. Well, 0.5 is right about here, right? And so that looks like it's about, I don't know, maybe 0.5-ish. It's a little less than 0.5, but it looks like it's about 0.5. Come in from the left, come in from the right, it approaches about 0.5. Okay, that's another one where if I had this function, I could have just directly substituted in. Nothing crazy is happening at 0.5. Let's look at 2. If I look at 2, I come in from the left and I'm approaching 2. I come in from the right, I'm approaching 0. Y value is correct. So we'd say that since those two limits, or since that graph goes to two different places, that limit does not exist. Okay, there is no limit, or the limit does not exist. Alright, here's a bunch of limit properties. Most of these are super straightforward. I have a handout that has all of these listed out for you, so you don't have to copy them down. I think there's even some examples on that handout. We're going to use these properties here in a minute, so if you need to pause and kind of look at them, study them for a second. We're about to use them right now. So suppose that I told you, and this is kind of a special limit that comes up quite often in calculus, but suppose that I told you that the limit as x approaches 0 of sine of x over x equals 1. Okay? Now notice if you put 0 in there, you get a 0 over 0 situation, so direct substitution doesn't work, but we can kind of analytically show that the limit as x approaches 0 of that function is 1. You could see it graphically also. We're going to use that fact to find and solve these two examples. So suppose that I looked at the limit as x approaches 0 of this function here, 1 minus cosine squared over x squared. Well, if I try direct substitution, it doesn't work. I'm dividing by 0. But if I use a little bit of what I learned in pre-calc, I can substitute sine squared in for 1 minus cosine squared. So I end up with sine squared x over x squared. Okay, and this is fine, but I still have that problem. Oh, and I didn't copy the limit down, but you should always copy the limit down until you actually take the limit. So the limit as x approaches 0. All right, and this is great, but I still can't directly substitute into this function. I'm going to rewrite this as the limit as x approaches 0 of sine of x over x squared. Okay. Now there was one property on the previous page that said that if I can take the limit of the inside, and that value is going to be the same as the limit of the whole thing squared. So if I take the limit of the inside squared, that's the same thing as the limit of that quantity squared. So I can take the limit of the inside and then square that. It's the same. So the limit as x approaches 0 of the inside is 1. So I'm going to plug in 1 and then just square that. Okay, because of this thing up here. In place of that, I can put a 1. 1 squared is just 1. So that limit is just 1 unit. Or, excuse me, 1. Okay, so let's kill that. Let's do the next one. We're going to use the similar reasoning. In place of this, I'm going to put 1 because I know the limit as x approaches 0 of sine of x over x is 1. And then I can use direct substitution on the rest. So I'm going to plug in 1 to the 9 plus 2 times 1 is 2 plus 7. Or excuse me, 0. 2 times 0 is 0 plus 7 is 7 over 0 plus 1, which is 1. So plus 7 minus 6. So 1 plus 7 is 8 minus 6 is 2. So that limit is just 2. All right. Let's go on to the next example, and the last example. The limit as x approaches 0 of 1 over x squared. Now sometimes we've got no tricks, we've got no rules that are going to help us. Sometimes we just have to look at it graphically. And we look at this one graphically, as x gets close to 0, so as I look in from the left and I look in from the right, notice that both of these values are going to the same direction. They're both going to positive infinity. All right. So if you were to look at y values as you got very, very close to x equals 0, you're going to see that all of those y values go to infinity, positive infinity. So we're going to say that this limit approaches positive infinity. Okay. Now some books will say, well, that limit doesn't exist, and the reason for that is infinity isn't really a number, so we can't say, hey, here you are at infinity, but it does give us some more information. Rather than saying it doesn't exist, we can say it goes to positive infinity, and that tells me that they're both going to positive infinity. If they were going the opposite directions, we would say that it doesn't exist. But since they're both going to positive infinity, we'll say, hey, this limit approaches positive infinity. And that's it for the beginning of limits.